Okay, we'll start our second part of the afternoon session by Stephanie from Vanderbilt. She will talk about hidden influence site.
Yeah, so I'm going to keep this super casual, mainly because I think I presented it in front of a good chunk of people, / 1/5 of this room is from Fraser Lab. But, I wanted to kind of ground and sort of start. So obviously a lot of the presentations that we've seen today really talk about sort of dynamics and dynamics across different scales. And oftentimes when we, look at a lot of dynamics, this is, looking at 3D variation across a cryo-EM, and especially outside of structural biology, this is the kind of dynamics that people sort of think about and think is important, and it totally is. But what I'm really interested in are these much smaller dynamics. And so really thinking about the different conformations that side chains and backbones can sit in, and how these really impact function. And these dynamics, while they're, a lot less dramatic and honestly probably a lot less pretty to visualize than these larger things, these are the dynamics that oftentimes are driving catalysis, are driving ligand binding, are driving a lot of the functions that proteins have to take on. And so if we think about sort of, just as a play example, if we have sort of the same residue and some sort of different perturbation, say a ligand bound or not bound or a mutation, oftentimes it can result in sort of a different distribution of conformations that we're able to capture in X-ray crystallography or in cryo-EM. But oftentimes in modeling in both of these techniques, what is placed on is sort of a single conformation of these side chains. And so what you have is sort of the model in the dark blue is placing sort of where the average data is really telling it to, but it really doesn't adequately capture sort of what is actually happening in the underlying ensemble, and it's hiding, a lot of the information of what the protein is taking on. And so what we're really interested in doing is saying, how can we be modeling multi-conformer models, which we believe much better captures this underlying distribution of conformations, and importantly, does it in a parsimonious way. So there are many different ways that you can represent ensembles, and hopefully I'll get to that towards the end of the talk. But what we really do is create these multi-conformer models in which you have multiple conformations or multiple coordinates of individual atoms. And so this can be on a side chain, this can be on part of a side chain and backbone up to sort of loop or domain motions. You then label the different positions with alternative conformation labels. So this alt A, alt B. And then importantly, also you label it, you give it some sort of an occupancy. And so you're saying how frequently in the ensemble representation of which is what you're getting from X-ray and cryo-EM is this atom in one position or another. And so, this can give us some information about sort of the Boltzmann ensemble of at least what we are collecting in this single experimental technique. But the issue with this is that to model these currently, pretty much you have to do it almost all by hand. And so you're going into COOT for those who have, modeled X-ray or EM structures, and you manually place the alternative conformations. Your eyes start to, get blurry after doing it for a while. And also there is sort of decision fatigue that happens when you have to do it manually. And so what a lot of my work was in the Fraser Lab was taking this out QFIT and really making a lot more robust and allowing us to do analyze alternative conformations, not on sort of a single protein scale, but really across the entire PDB. And so I'm going to quickly walk you through sort of the outline of QFIT. I will say it's open source and it's available at SP Grid and on our GitHub. But we initially do backbone sampling. We break the protein down into a residue by residue basis, do backbone sampling, and then we do coarse side chain sampling. This should be a video around the side chain. Oh, there it goes. And then we ask, how best can we fit all of these potential conformations that a side chain and a backbone can have to the experimental data? And so to do that, we use quadratic programming to determine the best fit between the map and the model. And so we do this all in real space. And so we're asking, okay, so we have some sort of observed density. And then importantly, from all of the potential conformations, we can calculate density. And what we are really trying to fit is sort of this weight parameter. How can we best weight all of the different potential conformations to best explain the experimental data? And so we also put multiple constraints on here to make sure that the weights can only be between 0 and 1. So that refers back to that occupancy parameter. You can only have certain amounts of different conformations that are explaining it, and that we want the sum of the weights to be between 0 and 1. And then we go back based off of our initial sampling, and we do really exhaustive conformational search in sort of selected spaces where the density is pointing us in.
This search is amino acid by amino acid, or,
Yes.
or a collection of amino acids.
No, it's we first do amino acid by amino acid. In this step, we also go in and we sample B factors in this smaller set. And I'll say that a lot of this algorithmic, I feel like I've had a couple of discussions with people today, but a lot of the algorithmic sort of decision making that we have here is all based off of this sampling problem that we have of sort of balancing out sort of the computational efforts and trying to sample as exhaustively as possible.
So that's not regular retention level.
No. And so after this, we go back and we do quadratic programming again, followed by a round of mixed integer quadratic programming to make sure that we have exactly a certain number of whole number conformations. And we also, at this point, apply a Bayesian information criteria. And this goes back to our principle of really trying to make a parsimonious model. And this is really embedded in sort of how we believe that this algorithm will be implemented in structural biology, knowing that there are going to be certain, sampling or modeling that we will almost definitely not be able to capture. I think there's no algorithm, currently that's able to capture. And so this is built to be really integrated with manual modeling still. And as I said, importantly, from this algorithm, what we also get is relative occupancies of side chains. And so you can actually weight each alternative conformation with their relative occupancy. And this gives back sort of estimate of sort of Boltzmann weight here from this.
So which is a typical size of the mixture? So how many different positions can it have? 2, 3,
So
10?
I would say typically it's 2 is probably your median, but we restrict it to be no more than 5. But you can really toggle this right, the Bayesian information criteria, and if you remove it, the median goes up to about 4 or 5. But oftentimes they were very overlapping conformations. And so, we had done this on a residue by residue basis. And so what we need to do is now put the protein back together. And so what we look for is we're really, at this point, we're just trying to understand sort of the conformations of the backbone and making sure that that is all physically connected to each other. And so looking at single conformations on sort of each end, and then looking at these structures of multi-conformer residues. And then we create these combinations. So for every single combination of conformers, we then do the optimization algorithm again. And finally, we end with simulating annealing to determine the appropriate labeling. And so this is going back to sort of how this is encoded, in which in the PDB encoding, an A alternative conformation can see an A alternative conformation, a B cannot see a B when they're locally together. And so you have to be able to label them correctly, knowing that sort of allowing that, an A conformation can go into the area that it, in clash with a B conformation.
And the number of labels is also determined automatically, or?
Yeah. And I should say, like for the number of labels, so usually I'd say there's up to a combination of 4 labels typically in our models. And so you can have an A alternative conformation sort of distally away from another A alternative conformation. It's really just making sure that this is not clashing when they're physically next to each other. Giving us a reassembled multi-conformer model. And so what we showed applying this across about 10,000 structures of the PDB is, and I should say high resolution, so in this case it's better than 2 angstrom structures, is that QFit generally improves the fit to experimental data. And so we're looking at this R-free parameter, which, going back to sort of validation metrics, is this really nice parameter that we, or metric that we can use in X-ray to say, are we actually fitting the data better by using, by having more parameters in our model and by fitting these alternative conformations, or are we just fitting to noise? And so everything below this red line indicates that we are improving the R-free. And so we see about a 2% improvement in R-free in about 81% of structures. And so, just to kind of orient those who are not familiar with X-ray improvements, the R-free is really representing sort of this error that you have between your model and your map. And so the majority of structures you have deposited in the PDB have this about 20% error that we're really not explaining. And there are many reasons for this. Part of it is sort of protein that we're addressing here. A lot of it is solvent issues. But there has been many efforts to be able to explain this data better, of which can explain it on individual proteins, but we really feel as though this is sort of the first time that this is kind of systematically or more systematically done. Yeah.
Do you find that the making R3 is dependent on the resolution of the structure?
No, but it tends to be very dependent on your input R values. Yeah. And so I think a lot of that's because we do everything in real space. And so depending on how well
Phases
are, I will say what I thought was going to be a slam dunk analysis was, what if we iterate through QFit and refinement? And it didn't actually really improve. Like, you got a big jump the first time, and then you never got it again.
So right now, is this your model's
I don't know. So I do think that it has to do with the bulk solvent, and even the modeled solvent gets really messed up with multi-conformer. And so I don't think you're actually fixing the phasing.
So I was just gonna say, so you're not actually refining anything other than the individual amino acid positions based on the existing density map? You're not changing, you're not refining the phases or anything like that?
So we are. So in this case, we basically took the deposited structures, put them through the same refinement pipeline as the QFIT structures. And that's what we are comparing.
Okay, so it's sort of like you re-refined it with and without QFIT.
Yeah,
on or off.
exactly.
Okay.
Yeah, to try to like, I mean, some of these structures are very old and it would totally be cheap system if we didn't re-refine them.
So
Yeah.
can I ask one more question?
Yeah.
So when you do this, do you like create an omit map or something for each, or a polar map or something for each residue? And
So-
then,
Yeah, we create a omit map for the entire protein.
for each residue,
No, for the entire protein.
what does an omit map for?
Yeah.
Okay, so
Just a Anderson map?
basically, and so they're like one of the things that we are hoping to try is if we, and this actually used to exist in QFIT pre my time, but if you do a polder or an omit map for every single residue individually and then go and fit it, would it be better? And this is also going back, the polder map idea is really going back to this like bulk solvent idea that it's likely hiding some of the data that we actually need to be fitting with alternative confirmations.
Any common themes for the ones where it got, like, the outliers that jumped up got worse with QFIT? Like,
Not that we can tell. Yeah, I mean, we looked at like size, sequence, other like crystallographic parameters. At some point I was like, I thought it was gonna be space group, but no, it's just. If anyone has any other metrics, I think we could throw at it.
I mean, I usually like to use CC3 over R3.
Yeah. So just visually sort of demonstrating, you know, these sort of, I say hidden because I think if there's anyone who does solve structures and they saw this, they would be like, these are not hidden at all, but hidden alternative conformations in high resolution X-ray structures. And so demonstrating that we can really recapitulate sort of the very obvious ones that leucine, but also some more subtle ones in the phenylalanine, which I think would be a lot more difficult to fit and determine by eye whether that is actually going to be a sort of quote unquote real alternative conformation that should be modeled and should be represented in the density. But we also show that we can improve model geometry. And some of this is a little bit cheating because how we are actually sampling the conformations are those that have perfect angles and perfect bond lengths. And so we are putting a lot of sort of physical priors into the algorithm. But even so, after refining, you know, it really keeps this. And so this is the mole probity score, in which you can see sort of that left shift of QFIT structures. And so just showing sort of one thing that it's very clear that we can improve on, which is really bond lengths and bond angles. And so attempting to sort of fit a single conformation in something that needs to be represented by multiple conformations, oftentimes you end up straining the conformation. And this is both on sort of how an individual person is modeling it, but with refinement, it's balancing sort of this fit to density versus sort of physical priors. But if you represent it with multiple conformations, and I'll say that the you know, ideal bond length is 1.791, we get much more, it's much closer to sort of the ideal. And then you're also, you know, fitting in these sort of tiny little pieces of density that again is really hard to pick up and determine by eye whether they should be fit. And so this is going, you know, have extended this to EM. and really showing that sort of as resolution improves, that we're able to identify more alternative conformations. And so this is going into, you know, I think issues that we have with EM. It presents a lot of additional challenges to creating multi-conformer models. The first is that resolution can be so varied across the maps that the way that people are handling maps and doing sharpening it's really all over the place, and it really impacts our ability to identify alternative conformations. And then we don't have nice metrics of saying, are we overfitting the data in EM? And so sort of our, you know, initial little bits of attempts of trying to solve these problems, but, you know, if anyone in the audience has feedback, I'm all ears. But, you know, for local resolution, we have implemented Q-score to be able to select models or residues to model. We've resharpened all of the maps using just Phoenix Auto Sharpen, so at least we're starting on the same page a bit more than using sort of a deposited map in which we don't know oftentimes unless you go and read the supplement, and then you're still lucky to understand how they're manipulating the map. And then sort of our overfitting is our big question.
Do you think it makes sense to resharpen the map according to the model that you are fitting?
Explain that more. I think I know what you're saying, but
so if you think that you have a better model,
yeah,
then you adapt the intensities of the map to match those of the model.
Yeah, it's just how do we get the initial model is
This is iterative.
yeah.
What stops the targeting community before you transforming the map and taking some of the coefficients and putting them aside for cross-validation like we do in crystallography?
Nothing like that is done.
Yeah, but I mean, that seems like you could, that wouldn't require any trickery, really.
Yeah. I don't know, but
Okay.
maybe, yeah.
Cool.
Maybe we just solved, I think, a huge, issue.
All right, for the naive, how would that be different than like the half map thing that people do of holding? Is that like holding out half the particles? Or
No, you could leave all the particles in. The question is like telling whether the model is overfit to the map, right? So you can take the map and Fourier transform it and mask some of the components before you back transform. And then you can see how well your model fits the held out set or masked set of Fourier coefficients.
so when people do like a half map thing for EM, what is that?
I don't know, I'm not an EM person.
It's just data precision.
I assume, yeah, is it more like CC half?
It's more like a CC half, yeah.
Okay, so with all these caveats, we wanted to see if QFIT could identify sort of conformational heterogeneity across a series of high resolution EM structures. And so this was taken from Basil Gerber's group over in London, in which he was able to get very high resolution, so about 1.8 angstrom of this kinase complex, which is really important. It's the CDK activating kinase, and it is what actually phosphorylates and regulates all other cyclin-dependent kinases. And so you have a CDK coming in with your cyclin, and then it needs to be phosphorylating by the CDK activating kinase in order for it to actually be active and then be able to phosphorylate whatever else it's doing. And so there's a lot of interest in trying to drug this, but given that it's a really large complex, it's not amenable to X-ray, as has been very successful with a lot of other kinases. And so what his group did is they took 15 potential inhibitors, and they got structures of them at really high resolution. And what we really wanted to do is ask, one, how can we model these high resolution structures with QFIT? Can we actually pick up on multiple conformations in EM, but also asking questions as sort of how does conformational heterogeneity change across these structures? And this is, really important because we go back to, I think, this, very common story that at least I get very interested in when you look at all of these different inhibitors or, different variations. You can think about it, different mutants of proteins, and then that they act in different ways, and then we overlay sort of their, alpha carbon, and it's like, okay, they look the same, and then some people are like, okay, well, I guess structure didn't tell us anything, and we throw it out. But as many people in this room are aware, right, that this is a single structure, and this is really not informing us always, or giving us sort of hypotheses of the function that proteins are going on. And so what we were able to do, and we were able to see a lot of conformational heterogeneity seen throughout these structures, and it was really highlighted by aromatic residues, where we would see aromatic residues in multiple conformations, and really importantly, because these structures were at sort of high enough resolution, when you had sort of single conformer, you even had, your little hole in the middle of the aromatics. And it looked very different sort of when you had these multiple conformations. And so that gave us, more evidence that we were able to fit these. And so this project is sort of, going back to work that I did a while ago, where we wanted to sort of classify and understand sort of how these different small conformational differences of proteins have impacting binding affinity. And so, folded proteins don't have a single state. They're dynamic, and they're always moving. But what gets me really excited about, the majority of the dynamics of globular proteins is that most of these dynamics are really side chains and backbones, and they're not disrupting crystal packing at times, and they're not leading to different sort of major classifications in EM. But they, once again, are sort of these dynamics that are really important in catalysis and in ligand binding. And so the multiplicity of the conformations that proteins have contribute to the conformational entropy of the protein. And what work really leading from NMR has shown us is that side chains accessing multiple different rotameric states or fluctuating with their rotameric states are really where this conformational entropy is sitting. It's much less in sort of the backbone or sort of large conformations. And when we think about this sort of coming from a statistical mechanic perspective, if you can create all of these different states by just these small fluctuations, right, that's where the majority of the enumeration of states is going to come in. It's not going to be a major conformational change of the protein. And so, as I said, NMR really provided some key insights into the impacts of conformational entropy, looking at how the conformational entropy changes upon some perturbation. And so this is comes from Babis Kalimotis' group back in 2012, in which they looked at this transcription factor binding to DNA. And so you can see DNA sort of at the top. And they asked, how do the fluctuations of side chains change when bound to DNA? And so anything that is, all of these spheres are probes that are put onto Bethel groups across the protein. Anything that's blue becomes more rigid upon DNA binding. Anything that's red becomes more flexible. And so it was very obvious that there was, these differences in terms of, how the flexibility of the protein changed. And then Josh Wan's group expanded sort of this idea of how we can apply these order parameters from NMR to conformational entropy by asking the question of how are they correlated with binding, ligand binding entropy. And so on the bottom here of this graph is going to be your averaged NMR order parameter across an entire structure, or your difference in your NMR order parameter. And then on the y-axis, you have ITC measurements, and then they estimate estimates of solvent accessible surface area and ligand rotational entropy. And so what they showed is that there is a decent linear correlation between NMR order parameters and what you could measure from ITC estimating the protein entropy. And so this is sort of, a really nice proof of principle that we can, that protein dynamics actually impact the entropy of binding, but that we have the possibility of actually extracting this information. But what I became really fascinated with is that, NMR really leaves open this question of how conformational entropy changes. And this really comes down to sort of this schematic that we have of the fact that you can have two different side chains, of which one is sort of between two rotamer states, or one is between three rotamer states, but when you read it out in sort of the order parameter from NMR, they read out very similarly. And thinking about sort of connecting this to a ligand binding parameter, you really want both the information about how much flexibility a side chain is, but also the exact positions that the side chains are in. And so we took this and jumped off of it, applying QFIT to a bunch of structures, and taking a previously developed crystallographic order parameter metric, asked how do side chains change, their dynamics change upon binding. Can we get some of this information from crystallographic structures? And so what we observed is that upon ligand binding, protein conformational heterogeneity differs a lot more in distal sites than in binding sites. So almost always in binding sites, what we observed is that, blue here is things that become less dynamic, red becomes more dynamic. Almost always around the binding site, you become less dynamic. But sort of distally or away from the binding site, you had much more differences. And so looking across about 700 different proteins, we observed that the greater the decrease in the binding site entropy, so the more loss of flexibility that it had, the greater the increase in distal site entropy. And so walking through sort of, the theory behind this is that proteins are almost always going to pay some sort of entropic penalty to be able to bind something. This is oftentimes very much in the binding site, but you sort of have two possibilities in distal regions. So you can also have a distal region that becomes a lot more rigid, and then the protein overall is going to have to pay this very large entropic penalty. But you could have a different scenario in which the protein actually becomes more flexible in the distal region, and then it's going to have to pay a much lower entropic penalty to actually be able to bind this. But we, on top of sort of the generalization of this pattern that we really think is embedded sort of in evolution, and we've been taking advantage of it. Medicinal chemists have been taking advantage of it sort of unknowingly for a long time. We really want to now say, how can we prospectively be designing things that are actually taking advantage of this? And so we looked across different structures of CDK2, so those are in the rows, and then all the columns are the residues, asking how different inhibitors impact conformational entropy. And so the first thing that we identified is that, there are sort of repeating patterns that we can see here. And we know a lot about sort of kinase dynamics and kinase inhibitors. And so we were really excited to see that this area that became a lot more flexible upon ligand binding maps to the activation loop, which we know becomes a lot more flexible upon binding type 1 inhibitors. And importantly, We don't see that for the top 2 rows, which are type 2 inhibitors. And so we call this sort of an entropic reservoir. We think that probably proteins have these areas in which when they have to bind to something, whether it's another protein or a ligand, that they sort of have to release their entropy elsewhere, and that they have some of these either reservoirs or sort of distributed entropy that it increases. But what gets me sort of really excited is that ligands can have these really unique conformational entropy signatures. And so how do we actually learn this and then design for it? So, you know, going back to our cyclin activating kinases, we wanted to ask very similar question of, is there any sort of conformational heterogeneity patterns that we can see sort of across these complexes, expanding this work really into EM. And so doing a very similar analysis, we observed that once again, you sort of have these repeating patterns upon ligand binding of areas that became more dynamic or less dynamic, but they didn't really map to any individual structures. And so right now, what we're doing is sort of going back and saying, okay, how do we actually identify these little pockets and what sort of signatures are incorporating in terms of how the protein and ligand are interacting and where the dynamics are coming in. But this is not the only heterogeneity that can exist in structures. And so, you know, the sort of next thing that we're tackling, and, you know, it's always a little intimidating to present work in front of the person who actually did the work. So I'll say all of the work that I'm about to present is Jessica's work, who's sitting right here, but modeling ligand conformational heterogeneity. And so, you know, proteins can exist in multiple states, but so can ligands. And this is really critical to understand, and again, sort of relating structure to any binding affinity metrics that you have, iteration of ligands, and really important for, I think, what is continuing to be a real, the real future of, or one of the real futures of structural biology, which is structure-based drug design. And so all this work is hot off the press. It was released last week, so you know, go and take a look. But what we wanted to do is ask questions of how can we actually model multiple conformations of ligands. And unlike with proteins, in which we sort of know rotamer states and we know these, you know, bond angles and bond lengths that proteins like to sit at, was for a long time a lot less information about ligands unless you were going to do a really expensive sort of QM calculation. But luckily, over the last couple of years, there's been a lot more sort of knowledge-based databases that have come out. And so what Jessica did is she took the experimental torsion knowledge distance database that can create conformations to generate different conformations of ligands. And so what this does is it's using sort of physical knowledge of the maximum and minimum distance between every single atom that exists in ligands to generate different conformations. But importantly, because we are specifically looking for conformations that are going to exist within a binding site, we had to do some sort of directed search of the conformation. It wasn't just any conformation that a ligand could take on. And so we put different constraints on generating these conformations, including restraining terminal atoms where they were initially modeled, restricting certain areas of proteins, so either restricting sort of these long branch portions of the protein, of the ligand, or restricting sort of the, you know, base of the ligand and letting the branch kind of move about, and then also doing sort of blob restraints, or sort of restricting within that binding pocket. And so we used the same mixed integer quadratic programming to determine this best fit to density based off of all of our sampled conformations. conformations. And so what we did was we were asking, how do multiple conformations of ligands improve the fit to data and improve strain? And so what we did is we took a set of true positives from the PDV and removed the initial conformation, asking, can we actually recapitulate this? And showing that, with multiple conformations, that we can improve the real space correlation coefficient. And this is occurring across many different ligands. But I think while, doing this in sort of traditional small molecules is exciting, what rethinking about sampling in this way allowed us to do is really address two new types of modeling. So the first is macrocycles, and macrocycles are sort of these, almost if small molecules and peptides kind of had a child, they would be macrocycles. They're these cyclic peptide-like molecules, and they're notoriously flexible, but the flexibility is actually what makes them really great. It allows them to be a lot of protein-protein inhibitors and fit into sort of flat grooves in proteins or between proteins, unlike small molecules that really need sort of that traditional binding site to fit into. But they're really hard to model because they're flexible and they're almost always in multiple conformations. And so we showed that we can automatically fit multiple conformations of many of these macrocycles, improving, again, the fit to data and often improving the strain as well. And I think sort of this strain goes back to very similar metrics that we had in proteins, where you try to sort of fit one conformation in where there should be two, and you can strain. And we've also expanded this to looking at event maps. So event maps, for those who aren't familiar, are maps that are made in sort of fragment or low occupancy ligand events. And so this is very commonly used in fragment screening or in drug discovery. And what you're trying to do is sort of identify both potential small, like very small fragments, so less than 300 kilodalton fragments, see where they bind in the protein, and if they bind at all. But what ends up happening is they end up being at really low occupancy. And so you can't actually detect them in typical maps. And so these Panda event maps allow you to detect the ligand density, but oftentimes because ligands are really small and flexible, they can actually sit in multiple conformations. And so we showed again automatically that we can identify these multiple conformations. And so with the 2 minutes or 3 minutes that I have left, I'm just gonna push on something that Andre actually touched on, but this is really sort of the encoding problem that we have. And so Andre talked a lot about sort of the PDV dev, and they've made an enormous amount of progress on sort of how to actually properly encode both conformational and compositional heterogeneity, thinking about it much more sort of coarse grain. But as I said, we're really interested in these small, subtle changes. And right now, the way that we actually encode them in PDV or in MMSIF models is really poor. And one thing to really point out is that, to me, is preventing us from using any of these encoding methods, whether they're, ensemble methods, whether they're multi-conformer, to have them actually be machine readable, to be able to do any sort of machine learning on them. Because the way that you can actually encode them right now is up to an individual depositor. It is not sort of uniform. And oftentimes, again, you have to sort of read the supplement of tables to understand what Alt A or Alt B or Alt C actually means. It's really preventing us from being able to use this data moving forward. And so, the first piece of this is that conformational heterogeneity occurs across scales. So I talked to you a lot about sort of different conformations of individual side chains, but when we think about sort of the data that we're collecting, we can collect conformational heterogeneity that is existing, on sort of a domain or, subunit level down to these individual conformations of, even just an oxygen, atom. But often it's integrated with compositional heterogeneity. And so you have to be able to encode and disentangle both of these. And there's been an enormous amount of progress algorithmically, but there hasn't been sort of the parallel process of being able to encode this correctly. And so right now, as I said, the only way that we can really encode conformational heterogeneity is with this Alt-A or Alt-B, this alternative conformation label. But this becomes, it's relatively simple in this scenario, but it becomes a lot more complex when you now have sort of a loop plus a side chain. So you have, this teal conformation. Okay, this is Alt-A, and then the purple is Alt-B. But then what do you do with this? And so right now, what happens is you usually have to duplicate all of these other atoms that are sitting in the exact same coordination, and then you'll label this Alt-B. But what this really misses is sort of this hierarchical information. How is the loop movement impacting the side chain movement? And how are these actually related to each other? And so we have proposed, and we've, I'll say that this is very much in the works with the PDB dev team, the Phoenix team, the CCP4 team, of how we can actually encode and also refine conformational heterogeneity across hierarchical levels by really encoding much more deeply different conformational layered states. And something that we're really working on now is making sure that we don't fall in the same trap of what we do now of not really knowing what Alt-A and Alt-B mean, but how do we be descriptive enough and flexible enough to allow people to encode this, but still have sort of enough restraints that it's something that is very machine readable. And then compositional heterogeneity is, can be encoded in very much the same way, where you have an Alt-B of the side chain in this sort of flipped up conformation that corresponds with the ligand being bound, and then Alt-A is very clearly, okay, the ligand is not bound, but the only way to actually encode that, okay, this side chain is associated with this ligand is again by labeling these Alt-Bs together. And this can be sort of, I used to sit next to, I'd say, one of the, or probably the world's most expert in modeling some of this stuff in fragment screening. And he was like, well, obviously it's always Alt-A is like without the ligand. And I was like, well, how am I supposed to know that unless I'm in your brain? Like, how is anyone else supposed to know that? And so how do we make sure that this is encoded properly? And so the biggest thing that we really need to do is sort of separate out this compositional and conformational heterogeneity. And so with that, I will close. The majority of this work was done when I was in the Fraser lab, but I just opened my lab up at Vanderbilt, and we are actively recruiting postdocs. So if this is of any interest to you, either entropy or how do we model things, please get in touch.
So how does this compare with like ensemble refinement?
So couple of like different ways. So, okay, encoding, right, completely different. We only have a single model in which every difference is just represented by alt-lock versus an ensemble, right? You can have up to, I think, usually it's like 20 different models. The other thing is that with ensemble refinement, and this is at least my experience, and I think other people's experience, it will do, right, it's a collective explanation of the density. But what oftentimes happens is model one will be real, or like, model one, model two will capture the dynamics in sort of region region A of the protein. And then in region B, it will like completely be unsolved. Like it's just like nonsensical conformations. And so that makes it really hard to determine. However, like ensemble refinement does a much better job than we do at backbone sampling. And so, but with multi-conformer, you can also go in, right, and manually edit and remove all alternate conformations in Coot as you see fit. And then I'd say like the other big difference is sort of the weighted parameter. We give occupancy versus there is no sort of weight of ensemble refinement. Although there is some sort of probability that I think they stick in the B factor column of ensemble refinement that is like the likelihood of fit of individual atoms, if I remember correctly, for playing around with it many years ago.
Go ahead.
Can you go to the plot of cross correlation at the beginning of Q-fit ligand? Yeah, that one. So how do you interpret negative cross correlation?
So it is a fit of the model to the map. Sorry.
My question is, if you have more degrees of freedom, I would expect that the cross correlation always increases. But it seems that sometimes it gets worse.
Yeah, so we can model into density that we shouldn't be modeling into.
I have a question about like when you try to optimize for the like occupancy or weights for the multi-conformers, how do you deal with the B factors? Because B factor also can explain the smear of the density, right?
Yeah, so in the sampling, we do sort of in a very naive way, we just we basically multiply the input B factor by different values. So I think it's like 0.2, 0.4, and we just use that sort of in our F calc, and then it can choose different B factors. It's not really, it almost never changes the solution that we're using, and then we really rely on refinement to sort of update the B factors. It's
So there's no grid search.
yeah.
Like after the multimodal like was introduced, I would expect the B factors to be smaller than the.
Yes, so after sort of, I should say QFIT oftentimes doesn't update the B factors when we do refinement, which is definitely using a more sophisticated way of sampling the B factors or adjusting the B factors. Almost always we see it reduced when you model an alternative.
To take over control while you answer another question.
Yeah.